The lesson today is a topic called impulse and momentum. Um, right off the top, momentum, this is sort of classic physics. Everybody from being alive, for as long as you've been alive, you've heard the word momentum. You could probably use it in a sentence. Um, if it came up in conversation, you'd be able to sort of roll with it and understand it. But technically, you haven't learned momentum yet. In a classroom with like notes and equations, we haven't gone over momentum. So it's possible that the ideas you have in your head about momentum aren't actually correct. So to help to sort of push through this, like sometimes I talk about physics education research, how professors at colleges have done studies about how people learn physics better. Momentum is a classic topic that comes up in these studies because of this exact reason. Since technically you haven't learned about it, maybe what's in your head is wrong. So, to make sure those wrong ideas, which are sometimes called misconceptions, to make sure we fix those misconceptions, you guys kind of need to be on your toes and actually a little bit self-aware. Is what I'm saying in this note match what's in your brain? Because if it doesn't, unfortunately, what you put in your brain over the years just learning about momentum isn't actually right. So, as you're reading, if something sounds out of sync with what you already thought, pause and think about it, because what that means is what you already thought was most likely wrong. Try and replace that wrong learning with a correct learning. To get you thinking about this topic, imagine this little game. Imagine we're at some sort of carnival or fair, and if you throw a ball at a wooden block and the block falls over, you hit the block with the ball, and the block falls over, then you win a prize. When we do the physics on this, what do you think would be a better option? If you're going to throw a ball that when it hit the block bounced off the ball, would that be more likely to knock it over? Or if you threw a ball that when it hit the wooden block stuck to it, would that be a better option to make it easier to knock the block over? So set up here, we're going to throw a ball, it's going to hit this block, and we want that block to fall over. What would be a smarter choice, to use a bouncy ball or a sticky ball? Think about that. We'll come back to it before the end of the little lesson. In Unit 1, when we talked about Newton's laws of motion, I said we would come back. We didn't really do much with Newton's third law. It's going to come back into play. But for today, we're going to backtrack to Newton's second law. I found this kind of interesting when I was doing my research for the note. Sir Isaac Newton was alive during the Great Plague that was decimating, that was killing people like crazy in England. Since he was kind of well-to-do and he had the resources, he quarantined himself. He went to his family's estate in the middle of nowhere. So kind of like what we're doing now, we're all sort of self-isolating, we're at home. When he was self-isolating, he didn't just sit on his butt. He probably sat on his butt, but he did a bunch of mental work. He basically invented the math that we now call calculus. So I'm sitting here at home, I'm binge watching TV, maybe I read a book, maybe I like walk around the neighborhood and go for a bike ride, but basically I'm just watching TV and being lazy. Newton invented calculus when he was going through the same sort of thing that we're going through now. Way back when in grade 11 and earlier in grade 12 when I reviewed Newton's laws of motion, I didn't really give you the calculus version because we couldn't assume that you could handle the calculus version. So we're going to go through Newton's second law again, but this time with this more comparable to how I actually wrote it than the calculus version of Newton's second law. Working backwards down here at the bottom of the chart, this is what we know Newton's second law to be. F net equals ma. If I bumped into you in the hallway and I said, hey, what's Newton's second law? Chances are you're going to answer F net equals ma. But that's actually a special case version of it. Newton actually wrote it using calculus notation, and it looked like this. If you've taken calculus, you'll recognize some of the notation, but it's not required. Just this is a calculus way. It's not exactly how he wrote it, but it gives you an idea. This crazy squiggly line, this is an integral symbol. So basically he said the integration of force with respect to time, so that's the integral f dt, is equal to the change, sometimes we call it, I'm just going to call it the change of m and v. So that's the dmv part. To switch out of the calculus notation, so notation you will have seen in high school, that integral sign, that kind of swoopy, it's actually an S, a swoopy S. We replace it with the sigma sign, which is Greek letter S. And the letter D, which is a calculus kind of notation, which is really the change in, we replace with the delta. So a non-calculus version of Newton's second law would be this. The sum of F multiplied by time is equal to the change in this MV product. Non-calculus, a little bit better way to write Newton's second law, a little bit more formal. Now what we often do, first of all, sum of F, we've done that all along. And if you look at other websites or textbooks or web pages, often instead of Fnet, you'll see people write Fnet. They'll write it as sum of F. I know Mr. Zare sometimes does it that way. Sum of F really, and Fnet really, they just mean add up the forces, taking into account the direction. So they're just literally another way to write the same thing. So sum of F really is Fnet. So that part, Fnet replaces, oops, that's a little bit messy. Fnet gets replaced, sum of F gets replaced by Fnet. If we divide the delta t to the other side, then we get this cool equation that doesn't match what we did yet, but it's closer. Fnet equals the change in mv divided by time. Now the simplification why Fnet equals ma is a special case is this sentence. Usually, but not always, but usually when something accelerates, the mass doesn't change. So since the mass doesn't change, instead of thinking it as the change in mv, we can kind of factor the m out of the change in step. So instead of change in mv, it's going to be m multiplied by the change in v. And then if we rewrite that, we got the m and the change in v divided by the change in t. That's grade 11 physics. Delta v over delta t is just what we call acceleration. That's this part. So in this special case, if the mass doesn't change, then Newton's second law, instead of being this cool calculus thing at the top or this non-calculus kind of weird looking thing here, if we assume that the mass isn't going to change, then Newton's second law turns into Fnet equals ma. But that is a special case. Can you think of a situation where as you push something and make it accelerate, the mass of that object changes? I'll give you a sec to think about it. Bad page break on my version to think about was in the next page. Okay, when we do this in class, if we could do it as a discussion, a couple scenarios come up. If we talk about a snowball rolling down a hill, the force of gravity is making it accelerate, but as it rolls, it picks up, so maybe classic cartoon physics, as it rolls, it picks up more and more snow, so its mass is increasing. We couldn't just use a boring old Fnet equals ma, because the mass would be changing. What mass would you use? The mass it had when it was small, the mass it had when it was heavier, some sort of weird average. So we'd have to do a little bit more work. We couldn't just use Fnet equals ma. Sometimes people, when I ask that question in class, they talk about like maybe a block of wood and it slides across something rough. And as it slides across something rough, it literally kind of shaves itself, or sandpaper sands itself. And as it slides, the block becomes lighter. Same idea, since the mass is changing, you couldn't use Fnet equals ma. What mass would you use? The heavy mass, the light mass? You'd have to use that more complicated version. The big example is my little SpaceX graphic here, rockets. When rockets are launched, they burn through fuel so fast that they're kind of like the block of wood sliding on sandpaper. Their mass gets lighter as they go. Since their mass is changing, they can't use Fnet equals ma to describe the dynamics, the forces on rockets. They'd have to use the more complicated calculus version. This is where the phrase, it's not rocket science, came from. Rocket science is more complicated, so if it's not rocket science, it's a simple situation. Okay, to summarize, to kind of wrap this up, the non-calculus better version of Newton's second law is this thing. Net force really, or force, multiplied by time is equal to the change in mv. Since that's kind of important, it got given the name impulse. So this whole equation, short form for impulse is capital J, is impulse. So really, impulse has two equations. So impulse could be, it's capital J, it's a vector. Impulse could be F times time. I'm going to be lazy and just call it F, but really it's like a net force, or it's the impulse of a particular force. If we knew, oh, give me a second, let me write the other one out. Or impulse has the second equation. It's still capital J, but it could be this change in mv quantity. This v is velocity, it's a vector as well. Impulse is most often used in collisions. So maybe you're going to civil or mechanical engineering and you're going to design a better airbag system in a car, so you're going to crash a bunch of cars in a lab. If you're crashing cars, you would want to know the impulse of those collisions. Or maybe you're going into sports and you want to design a better baseball bat so it puts more force on the baseball so the baseball will go farther. So you're going to look at the collision of the bat and the ball. You would want to know the impulse of those collisions. There's two ways to get the impulse, depending on what you know. If you know about force and time, then you would use this first version. You would say that impulse is force multiplied by time. Or maybe you don't know the force and the time, but you can figure out the speeds before and after the collision, or the velocities before and after the collision, and you know the mass of the object, so you know about the velocities and the mass. You could find the impulse using this version of the equation. One last thing, since this mv quantity shows up often, it got given a special name. It's called momentum. Momentum's given the short form of lowercase p. Don't ask me where that came from. I'm assuming it's like a language thing, but in another language, p made more sense. So when we talk about momentum, momentum's a vector, and it's equal to the mass times the velocity. So if we're talking about a flying baseball, if we knew the mass of a baseball and the velocity it was moving at, we could find the momentum of that baseball. If we're talking about a car driving down the road, if we know the mass of the car and the velocity of the car, we could figure out the momentum of that car. If we're doing car crash collisions, then maybe we figure out the impulse of a car crash by looking at the change in those momentums. So you'd look at the momentum it had finally and subtract off. Change in is always final minus initial, and subtract the momentum it had initially. These should be vector hats on there because direction becomes important. So a lot going on there, a lot of kind of new notation and things thrown at you. So here's a little summary here, working backwards from what we said at the end. Momentum is this thing, short form p, and it's found by taking mass multiplying by velocity. It doesn't have any fancy units, it's just mass units multiplied by velocity units. Impulse is really a version of Newton's second law, and it's got two equations. We can find impulse by looking at the force multiplied by the time, or the change in that thing that we called momentum. Depending on what you're given, use one form of the question, and then you can find impulse. That's really it for the note. There's a couple examples here with videos, so work through those examples, take a peek, see if they make sense. Bad page break. Go back to that original question, what ball would be better, the bouncy ball or the sticky ball? The solution is here. Take a peek at that too, see if your intuition was right. And there's a check-in and a worksheet related to all this. Hopefully that clarified things. As always, email if you have any questions.